This is from Winter 23, P41. Okay, and it's given us the equation that links the macroscopic quantities PV, T, and the microscopic quantities min KE, min square speed. Okay. There are only two equations that links this together, right? On one side here, you have PV is equal to nRT, PV is equal to NKT. But the bridge that links these two includes, for this side, pressure is equal to 1/3 rho C squared, or this form of the equation, because density is nm/v(c) squared. So I rearrange already, I get PV is equal to 1/3 nm(c) squared. If I compare this and this, which I think they want you to do later, you will be able to get the kinetic energy equation. KE would be equal to half mc squared, which is 3/2 nkt. For n particles, 3/2 kt for one particle. But first, you're asked to define the symbols. So the symbols for n is the number of molecules. Do not write short form in exam. Number of molecules or gas molecules. M is mass of one molecule. And C squared would be the mean square speed of one molecule. Okay, use the equation of state for the ideal gas to show that the average Ke, translational Ke of a molecule, at thermodynamic temperature is given by this. So just now I have PV is equal to 1/3 nm(c) squared. But also, based on the equation of state, PV is equal to NKT. Putting it together, NKT will be equal to 1/3 nm(c) squared. I can cancel the n. Okay. And then, up to you how you want to do it. I think I will rearrange. 3kT is equal to mc squared. And then I multiply by half. Multiply by half on both sides. So I will have 3kT, 3/2 kT is equal to half mc squared, which is equal to kinetic energy. Okay. You write this equation, 1 mark. You equate them, and algebra leading to this is 1 mark. Already 5 marks if you are familiar with the equation. Okay, part B. The surface of a star consists mainly of a gas that may be assumed to be ideal. Well. Okay. The molecules of the gas have a root mean square speed of this much. Mass of one gas particle is this much. Looks like hydrogen to me. Determine to 3SF. 3SF, pencil. The temperature of the surface of the star. Okay, well, we have this equation. I'm going to use the equation. So I have EK is 3/2 kT for one gas particle. Okay, so right now, this is half mc squared is 3/2 kT. And the reason why I want to write this is because I have the root mean square speed. All right, so the half can go away, and then this one I can put the 3.34 times 10 to the power of -27. C square would be 9300 square. Right, the half goes away. And then this will be 3 Boltzmann constant, 1.38 times 10 to the power of -23 T. Poke your calculator a bit. This will be 6980. Then I use my eraser to rub, just in case exam time I forget to write 3SF. I see 3SF very quickly, my pencil will come out and just doodle here at the side. Okay, so where be the marks? The marks will be at the substitution. Everything here substituted correctly, 1 mark. Then the answer written to 3SF is 1 mark. Okay. I want to point out here in this derivation section, right? The PV equal to NKT is an M1 mark. Those of you who are good in maths and have a tendency to skip steps, right? This is why you should not skip steps. Okay.
Miss,
Yes.
where do you get your K again?
There. Scroll, 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 scroll. Here.
Okay, thanks, Miss.
So we will always need to find, where was it? You to be familiar with the constant now. Okay. So we have the temperature. Okay, what was I talking about? Yes, please show this because this is the M1 mark. You don't write this equation, those of you who are very good at skipping steps, your class got a lot. Then you will forget, you will lose this mark lah, you lose mark here and there lah, because you never show the complete working. Okay, so show, don't skip. Whatever you substitute inside here should be numbers that I see inside the question. If I need to do additional calculation, I also have to show that, even if it's divide by 2 or multiply by 2. Show it. Okay, part C. The radiant flux intensity of the radiation from the star is this much. Wow, suddenly whiplash to the last chapter. So radiant flux intensity is F, but it's still intensity lah. F will be, intensity is power over area. So luminosity over surface area of a star, 2 pi r, 4 pi r squared. Where the observed distance is this far from the star. Calculate the luminosity, give a unit for your answer. F is equal to L over 4 pi r squared, or 4 pi d squared. So from here, if I want to calculate L, I will take F, 2.52 times 10 to the power -8 times 4 pi, and the distance is 4.16 times 10 to the power 16 square. From here, you can calculate luminosity. Let me check my answer. I press correctly. 5.48 times 10 to the power of 26. What? So radiant flux intensity is still intensity. Intensity is power over area. Okay, so please don't come up with weird names. Or you could see there's a unit here. Watt per meter square. So L will be what? Right, next part, determine the radius of the star. This one need to borrow the Stefan Boltzmann equation. If you scroll to the front of the question page, scroll, there's a Stefan Boltzmann law equation here. Luminosity is 4 pi sigma r squared t to the power of 4. And we also have the value of sigma here. Stefan Boltzmann constant, this is sigma. All right, so I'm going to use both the equation and the constant in my question. So L would be 4 pi sigma r squared t to the power of 4. I have L, 5.48 times 10 to the power 26. 4 pi, can put in the value of sigma, 5.67 times 10 to the power of -8. R squared, temperature, how hot is my star? 6980. It's a very hot star. All right, I put my calculator. I will get 5.69 times 10 to the power of 8. Because significant figure is inherited, so the first significant figure that we calculated is 3SF, everything else is 3SF. Write extra SF, no harm. Okay, so for this calculation section, for the first one, you write the right equation is 1 mark already. And then the substitution, the answer, the unit is 1 mark. For the second one, they won't give you mark for the equation because you copy from the front page. So the mark will be for the substitution and the final answer. Right, finally, 3D. The gas at the surface of a star has very high pressure. Okay. Because they are moving very fast and they collide more with each other. Okay. Using the basic assumption of kinetic theory to suggest why in practice, a gas at the surface of a star is unlikely to behave as an ideal gas. So the main assumption of ideal gas is what? No intermolecular forces. So ideal gas has no intermolecular forces. AKA no bonds, no covalent, no hydrogen, nothing. Just no bonds. They do not talk to each other. They do not exert force on each other. They do not attract, they do not repel. Okay. So this generally happens for ideal gases when they are like super far apart. The electric field of the electrons from particle A will not interact with the electric field of the electrons in particle B. However, right now it's very high pressure. So what happens to a particle? They are very close. So use their language again. At very high pressure, the gas particles are very close together. Adopt the energy of the question, as the Gen Zs will say. Basically, the question say very high pressure, then you're like, okay, very close together. Don't just write nearer, don't just say come closer, but they are very, very close together, okay? And because of this, because they are so close, right? Imagine this is the nucleus and you got all the orbital electrons. So your electron will disturb my electron, no? Let's say there's another particle here, and we're very close until our orbitals almost overlap. So your electron will confirm disturb my electron one. We will repel, we will attract, van der Waals, there is a dipole moment, all the chemistry stuff will come in, but basically they're too close together, okay? So because of this, the forces between the gas molecules are no longer negligible. So this is the assumption of kinetic theory. Another way to talk about this besides the forces is the volume. It's because they are very closely packed. I can say that the volume of the molecules no longer negligible when compared to the volume of the gas. There's no container here. The sun is not a container, or rather the star is not a container. Although what is a container? Okay, let's not go there. So 1 mark would be you mentioned the particles are very close together. And because of this, the forces, the intermolecular forces is no longer negligible, P1. Or you can say the volume is no longer negligible, but this one need to compare when compared to the volume of the gas. Because we assume the force is 0 for ideal gas. Okay. The ER say candidates found this unusual application of the assumption of ideal gas to be challenging. Okay, unusual. Many students did not write the first. Good thing they put B, right? If I said question, I very savage one. I go M1A1 and then GG. Then you will get 0 or 2. So they put B is good. Being nice to you. Okay, so that's the gas question for the winter 2-3 series.